for Adyen. So what do I do at Adyen? I analyze payments. Like, I started to work with Spark approximately 4 or 5 years ago, and it was the perfect use case to analyze viruses because it was integrating Python, tool stack, which was having a lot of ecosystem to analyze malware. So here at Adyen, I decided to use Spark because it had a lot of tool stack to utilize machine learning, which is also Python. So we started to do analysis in Spark. So a lot of things is possible to be done in Spark, and we wanted to simplify the work of a data scientist. We wanted to make the data scientist workflow quite secure, quite nice, and it's a typical flow. We have a group of people accessing the data through browser. Well, what could be actually complicated in this flow? Well, it's not that simple, apparently, because we wanted to know what kind of columns were used together, or if people were actually looking at the data that they are allowed to look at, or if people are actually aggregating the data the way they are supposed to be aggregating the data, or they are doing something completely different out of their profile. That was difficult. As other nodes, we really wanted to know, like, okay, we need to know what columns are accessed, which columns are not accessed, which data is actually accessed, and which is actually stale, because in managed notebook environments, besides we have on-prem infrastructure, so having on-prem infrastructure really cares about space. So we wanted to know if people are uploading CSV files, and if they are actually using them, and how they are using them, etc., etc., etc. So really, we wanted to track the data lineage and know the normal and abnormal usages of data by profiling everyone, by profiling every one of the peer group, and by profiling it by usages. So these were kind of the graphs generated by our lineage tracking notebooks, and it clearly kind of groups those many people into same clusters just by the way they look at data. So to speak about our technology stack that we use for data science within Adyen, and it might be really familiar for you. So we use Jupyter Hub as the managed notebook infrastructure because it has very nice authentication, it has containerization, and it manages our notebooks. Obviously, it's Jupyter Hub, and it's Apache Spark with some heavy customizations done through Java agents, and our own customizations to Jupyter, notebooks, and libraries, etc., etc., etc. We also use our own homegrown ETL pipelining tool, which is modeled like Apache Airflow, but it's simpler and smaller because we didn't want to have full Apache Airflow. So you may ask, like, you have a perfect use case for Databricks, and Databricks is a really awesome product, but 2 years ago when we were starting this project, Databricks was not running on-premise, and our hard requirement was running the notebook infrastructure on premises, and going to cloud was not an option. I don't know if Databricks supports on-prem run mode, but probably it doesn't still. So we are stuck with this tool stack for now, and we're actually quite happy about it. Did anyone here use Jupyter Hub infrastructure? Cool. Do you like it? Oh, wow. I see mixed feelings. I share opinions. So how our setup is actually looking like. We have Jupyter Hub on the top. That's really the API gateway for notebooks. Then we have a bunch of single user servers, which start kernels drivers per every notebooks. So basically, in our case, every different notebook has a kernel, and every kernel has one single driver. This is a bit different from Databricks setup, where the the setup is that multiple different notebooks can be communicated to the same driver. Though we're running on-prem, so we cannot really launch individual clusters we cannot really launch individual clusters of random size, etc., etc., etc. We have just dedicated bunch of servers where we run our data science. So everything is communicating with the Spark cluster, and we store the data on HDFS, and we have some other data sources outside, and we have our managed application infrastructure, which is our Airflow-like ETL. So Airflow-like ETL is very easy to track because we have, well, a few hundred of jobs, and they're all related to each other, and we know what job is dependent on what and how the data is generated from exact jobs. But the real kind of tracking problem is tracking the usage from Jupyter Hub, single user service, kernel drivers, to Spark cluster. So users can be actually creating data sets by running a join of billion by billion or more and whatever, and saving it to HDFS. Then other users can be reading that snapshot and running their machine learning analysis on it, or using the data. And without having a data lineage, we have been completely blind. Like, okay, so someone dumped a dataset on HDFS, and we don't know how it was generated. Yeah, a file, a Parquet file. We don't know. So we had to store that somehow. And it was actually quite challenging, keeping in mind the fact that files could be uploaded to HDFS through Jupyter Hub. So someone can take a CSV from somewhere and upload it, put it in HDFS, join it with our managed data sources, and produce some reports. So we really don't know what's in that CSV, but at least we know the column names of that CSV, and we see how that is aggregated. So yeah, nice. We know what people are doing. So does anyone here know more or less how Jupyter protocol works? Raise hands if you do. Oh, cool. So probably it will be interesting for most of you because I didn't see a lot of hands. So Jupyter protocol is a very big and fun WebSocket mesh that communicates in messages like this. So Jupyter protocol is interaction between 3 processes. One process is your browser. The other process that Jupyter protocol integrates with is the notebook manager process, or single user server. So when you're launching a notebook on your local machine, which we don't want to do, but let's say that's how Jupyter is working sometimes, you have a notebook manager and kernel manager. So they run in one Python process. So we are running that in Jupyter Hub single user server process. Okay, cool. So that's one process. And we have another process called Jupyter kernel. So within Jupyter kernel, we have IPython, very nice library. Then we execute the user code over there. And we execute Spark and other stuff like scikit-learn, NumPy, pandas, whatever. And here's how we're accessing data. So the main difficulty and work is happening through 3 main threads of a kernel. They are called IOPub, they are called communication thread, and they are called control thread. So all of the work that is done in a Jupyter is done through 3 threads. Well, actually 5, but important ones are only 3. And on the format of every message, we can say that every message coming through this thread, through this Ethereum queue sockets, we have message with content, message with type, and every message has actually unique UID, and every message has a different one, and session UID, which is the same for every open notebook in a browser. So if you open 2 notebooks in a browser, they'll have different sessions, but actually they will be communicating to the same kernel. So it was very difficult to discover it initially or wrap the head around, but that's how Jupyter works. And yeah, so what do we do actually with this? So remember this: message ID, message type, and session. It was easy. So we just intercepted Jupyter client library, and we added some audit logging tracking, and we dumped it into syslog, and then we were able to track it. So, but we were only able to track what people entered as a code and what people did receive as the output. But yeah, that's what that's where instrumenting of Jupyter Hub or in Jupyter protocol ended. Then we actually wanted to know how people were actually working with data. So as we know, Spark runs on multiple different processes. And none of the existing solutions in the market that we were looking at that moment of time when we started this was actually able to explain how people were aggregating the data and what data they were looking at. So what we were interested specifically, the kernel process, which was the PySpark submit job, the driver, had instrumented execute input section. So basically execute input is something within a Jupyter protocol responsible for taking the user code and then executing that. And okay, so how we solved it, we took the context of a running Spark application and we did set local property, and here's how we were telling that the code within the cluster of Spark is actually tied to this whole execution down the line through all of the workers and executors by this given message ID and session. Okay, what was happening next? We were instrumenting Spark context and its listener bus to start dumping execution plans of the driver and other things. The interesting thing is execution plan. So every time you submit a DataFrame job, you have fairly large, if you're using machine learning algorithms for the analysis, etc., 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 you have fairly large DataFrame computation graph, which is dumped every time. And basically, this is one of the main sources of us looking on how people are analyzing their data, because execution plan contains how the data is aggregated, if it's broadcast hash join or if it is the stored merge join. And it tells us what files were actually looked at. Cool. So that works. And to answer the question on what files were created, we had to do some very interesting technique to instrument a class called insert into Hadoop FS relation of Spark to get an instrumentation event every time the file was created on the storage by Spark. So everything from here related to the Spark side was thrown into the audit log, which we later were analyzing. So this was useful, though it was very complex to implement, and we were really looking at different solutions. Well, okay, yeah, we know how to do it. We know that it's possible to do it this way, but it's actually a lot of work. We either are ending up forking Spark and patching it and running our own fork in Spark, or write Java agents and patch it in runtime and deal with it. So we really wanted to explore some other options to actually start going this hard way. So there were a few interesting projects on tracking data lineage in context of Apache Spark. The first one, the interesting one, was Project Ition. If you have a phone, actually take a picture of the slides and read this paper. It's a very nice and interesting description of deep analysis, how researchers thought would be the best way to analyze the data lineage of Spark. Their approach was to take every RDD, take every reduce, take every map stage, get a snapshot of the data flowing in, and just dump another dataset on disk to know the state of data at exact point of data transformation pipeline, which was something that was too much for us. We had a limited capacity on hardware, and we didn't want another terabytes of data per day created by just lineage log. I mean, it's smaller. So Ition was a very nice project for idea inspiration, but it was still not good for us. The other thing that was worth looking at was project Big Debug. Probably also take a picture of it, and at least it's a funny name. So Big Debug as a project was aiming at knowing where my MapReduce job did go wrong and what do I need to tune. It was doing it very well, but it had closed sources. So I was not able to find any sources online to actually look at it. But I liked the idea, and I liked the way they described in the paper. And actually, that's where I learned about insert into Hadoop Fessler relation to implement it within Lineage. So thanks to these guys, kudos. Take a screenshot, read this paper. It's very interesting for those who want to know about Spark internals. Though it's about Spark 1.6, so it's not that useful, but still it will satisfy your technical curiosity. The other things we were looking at were the Cloudera Navigator. So Cloudera Navigator actually had the best data lineage user interface in the world at that moment of time. So to be clear, it was around October of 2016, so a bit like 2 years ago. So Cloudera Navigator was working very well. It was tracking data lineage. It was satisfying 100% of our requirements, except it was actually being part of very big commercial distributions that we didn't really want to take on board for the start. But the downside of Cloudera Navigator was that it was not supporting Spark, and it was not supporting interactive analysis. So we decided not to take Cloudera Navigator, but it has very nice UI. Well, yeah, it's true. Then we were suggested by many people, well, okay, yeah, guys, you're exploring this security stuff. Why don't you actually look at Apache Ranger and Apache Atlas? Well, the answer was that at that moment of time, we wanted to keep a number of moving parts in our ever-growing ecosystem to the necessary and reasonable minimum, and not introduce new bunches of JVMs into infrastructure without a great need. So we actually thought that, well, okay, let's actually implement a Java agent instead of supporting and deploying Ranger and Atlas. Well, Atlas is still not supporting interactive data analysis, but maybe if we eventually decide to use Atlas, we would actually forward the data collected with this thing to Atlas. But it's too complex, and it didn't have a UI back then. We also don't. The other things worth mentioning that we looked at were projects of Driven.io. Driven.io is an awesome project for batch processing jobs. So if you're looking for a commercial vendor that is visualizing data lineage for your batch jobs, go for Driven.io, because it's helpful for getting your performance of the jobs monitored in a very nice and enterprise way. Then if you are really distancing yourselves from any commercial solutions, you can go and take a look at a solution called Apps Spline, which was presented at Spark Summit in 2017, year after we started this data lineage project at Adyen. And Apps Spline is a very nice data lineage and a tool for tracking within Spark jobs, which works very well for bad jobs, but not interactive data analysis. And it has very nice UI, but it does not support interactive data analysis. So those were the things that we looked at. Maybe the crowd over here can tell about something else that we missed looking at. Okay, so to describe the difficulty of the problem, we can be looking at our analysis pipeline. So every time anyone was entering any code, it was getting as Jupyter execute input message. It was getting to Jupyter kernel, and within Jupyter kernel, the driver calls were actually made, where stage submitted and SQL execution plan events were generated. Basically, stage submitted is something that we were getting from Spark context listener bus every time we were getting RDDs into execution, or actually execution start. And SQL execution plans were actually gotten when we were doing DataFrame queries. So as we expect, staged RDD execution plans and DataFrame execution plans were actually quite different, though as the later stage we actually figured out, well, at one stage of notebook execution, we were making a custom data frame based on RDD. And we knew the structure of the RDD, and then we joined the data frame originated from RDD with another data frame originated from our metastore manage table. And we're able to link the origins of the RDD to the actual aggregation happening on the code. Cool. So we knew the origins of RDDs, we knew the columns projected, etc., etc., etc. But what was happening in the executor side of Spark job, sometimes data scientists were creating temporary datasets. So we had to actually keep track of that. And for that, we had to instrument the executor to get some aspects around insert Hadoop FS relation. And obviously, it was done through Java Agent API, and we used code instrumentation to actually know what was created from what, and from what Python code entered, or Scala code entered. It doesn't really matter. If you may ask how we were actually linking all processes together, so Spark Context has a very nice feature which is called context properties or local properties. So Spark Context properties in a driver is represented as thread local map, and it's replicating its values every time we access a context from different thread. Though, on the executor side, these properties are no longer called local properties, they are called task properties, or they are called job info properties. So we had to tune our correlation of audit log messages accordingly to join stuff together. But every time there was a message without audit enabled input, So let's say a job which was really non-authorized in deployment process or something like that. Executors were failing the entire driver by telling message ID not found, canceling on jobs. So basically, using Java agent instrumentation technique, we were able to gain prevention of executing of non-audited code on the Hadoop cluster. And it actually works fine. Do you want any more details on that? Yep. Could you repeat the question, please?
How did you annotate the non-audited code? How did you know to filter them out?
So audited code didn't have the message ID property. So Spark jobs and Spark tasks that did not have properties of the certain kind was not.
Can you use the same mechanism to filter out the parts of the lineage that you don't want?
Yes, but then we need to actually encode more information into the message, and it will make it bigger and harder to manage. So we can, obviously.
So the lineage that you're capturing is actually not based on. It's based on the actual code. It's not based on some annotations or some explicit documentation.
No, it's actually really unsupervised lineage capturing.
Then how do you filter out all the clutter? Because then you get big pipelines. That's the discussion. So
Yes.
you get a lot of information.
Yes, we get a big pipelines here, and we just keep it indefinitely and use it for multiple different useful and useless purposes. So, any other questions? Okay, so after we were executing the job on the worker side, we're actually getting back to presenting the data back to the user. So Jupyter protocol is actually quite consistent in the ways how we can terminate the message. So every time you execute the code, you always have execute input. So logically, you think that in the end of this whole process, you'll have execute output or something like it, or show result. But the protocol itself actually can stream you the results back when it's an image, or if it's SVG graph, or matplotlib, whatever. Or it can display data, which is a text, or there could be some other multiple different end message termination states, which was very hard to manage. And that actually required us creation of entirely dedicated data pipeline for correlation of audit log messages. Like, you know, every message which is coming from a different process is a separate event. It's a separate entry on your audit or in your database. And you cannot really create easy monitoring on really sparse structure. So our alerting infrastructure is really based on Elasticsearch. So we were asked to correlate this all into an Elasticsearch-friendly document. So basically input, output, execution plan, all of the sessions and all of the queries that could be happening inside of the worker cluster had to be placed into one big JSON. So we could know that if there was word foo in the code and there was word bar in the display with word buzz in execution plan, make the alert. So here is how we implemented it. We had few queues that were dealing with this real-time graph. And basically, it was just 5,000 lines of Python code, nothing much complex. And we were taking data from one pipeline and putting it to other pipeline, and that's it. And yeah, maybe you can take a picture if you want to implement your data lineage solution at home. Here is the blueprint. So that was basically it. Adyen is hiring data scientist and data engineer. Take a look at this link at the website. And here is the time for questions. So